All righty, I will share my screen. And let's see. Oh, well, that didn't work. Let me try again. Share screen. This is what I want to share. There, much better.
We can see it, but if you want to use that presentation mode, there you go.
There we go. All right. Yeah, well, thank you all for spending the next 6 hours with us. But I will shorten it to 1 hour because I'm very clever that way, and that should be advantageous to just talk about this in 1 hour. Well, one of the questions that you might have right off the bat is, what is heliophysics? Because that's sort of the nature of this heliophysics big year, which is what we're calling this. Basically, it's the scientific discipline that deals with essentially everything that the sun does, from the core all the way out to interstellar space. It's basically a description of how the matter and energy in the sun flows out into the rest of the universe. On the way there, it brushes by the Earth and the planets, and sometimes wreaks havoc with their magnetic fields and other things. We're particularly interested in heliophysics because, we have a lot of assets in space, and we have a lot of astronauts working in space, so we need to keep up with what's going on in the environment that they're working. And heliophysics is a subject that lets us figure all that out and start making predictions about when we're going to have good events and bad events for our astronauts and our technology. So the heliophysics big year, this is a kind of a synopsis of the timeline. Nominally, it started with the annular eclipse in October. It passes through the April 8th total solar eclipse, which we're all waiting for. And then it concludes with the Parker Solar Probe's close approach to the sun next December 2024. So it's a 14-month span, and we've already gone 1 month into it. So this is November. Each month has a different theme. That's, as you're going to experience, pretty diverse in terms of topics and approaches. We have a monthly theme about fashion, although when we get there, it's not going to be quite what you think it is. But we're going to have fun with the whole concept of assigning a theme to each month. And here's kind of a list of the upcoming themes. Right now, we're talking about the heliophysics mission fleet. That's today's talk. December, in about 3 weeks, we'll be talking about citizen science. January, the sun touches everything, and well, you can sort of read the rest. There are more themes extending to next December, but there was not enough space on this slide to really include them with a reasonable font. So I will keep you in suspense. NASA is sort of all about big questions, as you can well imagine. And the 3 big questions that it's come up with for the area of studying the sun and heliophysics is, what causes the sun to vary? How do Earth and the heliosphere respond to those changes? And what are the impacts on humanity? We call these the big questions because they seem to summarize a whole number of discoveries in various categories and sort of organize them around some central themes and questions. Of course, the scientific research into these areas is far more granular than these big questions suggest. But that's why we have professional astronomers, because they can come up with 1,000 more questions than the 3 here. But these are pretty good working questions to start from. And so that's what we're going to use for this 14-month sort of session. The neat thing about these big questions is that we can relate them directly to national education standards. And Christina Millot and Hilary Davis and myself and a few others have spent a lot of time trying to figure out how heliophysics concepts map into the national science standards. And so we've created a framework for heliophysics education, which sort of reflects how the big questions map into the standards, which are given sort of in parentheses at the end of each of the sub-questions, what kind of guiding questions underneath each of the big themes. So we've kind of organized this as best we can. You know, if you want to have a look at the actual framework, as we call it, that's on our NASA HEAT website, and I'll refer you to a URL for that a little bit later. Well, anyway, so this month's theme is NASA's fleet of spacecraft. We have about 48 or so operating spacecraft and missions, and their locations extend everywhere from inside the corona of the sun at this point with the Parker Solar Probe, all the way out to the edge of interplanetary space with the Voyager spacecraft. If you can imagine how big this volume of space is that we're talking about, one astronomical unit is 150 million kilometers. It's 93 million miles, and that's only to get to one astronomical unit. And we're out here at 120, looking at the world from that vantage point. If you calculate the number of cubic kilometers involved, it's trillions upon trillions of cubic kilometers. And we have 48 satellites that are making measurements where they are from you know, a variety of vantage points. And from these 48 spacecraft, we are trying to build up a picture of how the entire thing works. How the heliosphere, which is the volume of space touched by the sun's solar wind, how that interacts with the planets, how the sun produces sunspots and flares and coronal mass ejections and a variety of phenomena like that. And also the interior of the sun, which you could imagine is sort of an untouchable area, but we have techniques that are like seismology, which allow us to actually understand what the interior of the sun looks like, which to me is just the most remarkable thing that we do. Anyway, I thought about how I was supposed to talk about 48 different missions with 48 different science approaches and goals and instruments and things like that in simply a 1 hour talk. And I realized there is one thing that sort of organizes all of these together into one general problem. You know, you've got a satellite or a spacecraft that's millions of miles away from the Earth. It's gathering up all kinds of cool information. It's taking images of the sun's surface. It's measuring magnetic fields where it happens to be located. It's measuring and inventorying the kind of particles that it finds near it. And it's converting all of these things into numbers. But essentially, unless those numbers get to Earth, the spacecraft might just as well be a black hole, right? It doesn't matter if the thing is making the most fantastic measurements in the world. If it's not telling you about it, then it basically doesn't exist. So the challenge is, how do you get this information from the satellite and spacecraft down to the Earth where scientists can start analyzing it, looking for patterns and things of that sort? So these instruments, you know, they're generating lots of information. And so what I'm going to talk about this evening is the scale of that information and how it gets relayed back down to Earth. That seems to be a fundamental thing that is shared by all of the missions. In terms of the big questions and the guiding questions and the standards, what's highlighted in red is a standard and a set of standards and a question which are the closest match to what I'm going to be talking about. We're going to be talking about communications technology. The implicit assumption is that if you're sending radio waves across the solar system better be well behaved and not stormy. Otherwise, your signals are going to get corrupted by flares and things like that. So communicating information across the distances in the solar system is manifestly going to have to depend on the character of space weather, as we call it, the level of storminess of the sun. So those things are all kind of integrated together in a kind of a nice way. Okay, here's what's quite interesting. The entire constellation of NASA missions collects terabytes of data every day. I mean, a terabyte is 1,000 gigabytes. 1 gigabyte is about the storage capacity of your cell phone. So every day, about 1,000 cell phones worth of data are collected by these NASA satellites and relayed to the Earth. All right. So what we're going to do is take a look at how that works. First of all, let's look at like images. Images are sort of the easiest to understand because whenever we snap a smartphone picture of our cat, which is what most people do, we're creating images that are collections of pixels. Each of those pixels corresponds to a particular X and Y location within the image, row and column. And the pixel is characterized by how bright the light is in the red, blue, and green bands at each pixel. So these numbers, there are 3 numbers per pixel, and typically 1 million pixels per image. So you can already see that just snapping one picture generates quite a lot of numbers. The next step that the satellite does, if it's taking images of things, is it has to convert each of those base 10 numbers into a binary code of ones and zeros. Now you might wonder, why is it that we settled on binary arithmetic to communicate information? Well, binary numbers are absolutely the coolest things in the world because each number represents a switch that's either on or off. If it's off, it's 0. If it's on, it's 1. So if you think of these as switches being set, binary numbers correspond exactly to the switches in a integrated circuit or switches in a computer. And so it's a natural way to represent base 10 numbers in terms of the positioning of switches in a sequence. Here's an example. I can't really see it too well because I have a lot of menus that are covering it, but oops, I'm sorry. I took one of these numbers on that green screen. I think it was 011011001, and I converted it first into its base 2 numbers, and then finally the decimal number is 105. And so every one of these numbers that you see in the column represents a base 10 number, which perhaps would be the intensity of light falling on a particular pixel in the green band, or in the red band, or in the blue. So that's how this works. Now, these strings of on and offs are transmitted to Earth by the spacecraft. And so the transmitter is on when you receive a 1, and the transmitter is off when you receive a 0. And this is sort of what the telemetry looks like when it finally gets to Earth. It looks like a very ratty looking signal. You can see the 1 is kind of ratty looking. It's got squiggles. And then when you get to 0, well, it goes way down, to the bottom, and it's still kind of ratty. And then for the next 1, it comes back up, and the signal is still kind of ratty. It's not clean. It's not like it's 1 across the whole thing and then goes to 0 across the whole thing and then goes to 1 across the whole thing. But because these are telemetry signals, radio signals from a distant spacecraft, they're going to have noise in them. And so the problem is when the noise gets too high, you're not going to be able to discriminate between the 1 and the 0 because the noise is going to wash out the difference. So when you transmit data across the solar system, long distances, you have to be very careful that your receiver can discriminate between the 1s and 0s that are being sent. And as we'll see later, there are a couple of ways of doing that. Ground stations receive these binary on and off things, but the signals are so weak that you need really large radio dishes like this in order to gather up enough energy from the signal to actually discriminate between the on and the off state. All right. The transmitting antenna on the spacecraft might only be about 1 meter across because that's set by the weight and the cost of the satellite. So it's only transmitting with a very, very small antenna across the entire solar system. So in order to detect that signal, you have to make up the difference by having a really big antenna here on Earth to gather up the energy to be able to discriminate between a 1 and a 0. So that's why the Deep Space Network, this is one of the instruments in Canberra, Australia. We use very big dishes to communicate with interplanetary spacecraft. Here's an example of what one of these signals actually looks like. You know, at the top, it's 1 for a while, and then it goes to 0 for a while, and it goes back up to 1, as you can see in the green sort of trace. Down below in the blue, you're seeing what the actual signal might look like. It doesn't look anything like this nice square-looking thing. It's kind of ratty looking. So the electronics in your receiver have to be able to clean up the signal that looks like the bottom thing and turn it into something that looks like the top thing that a computer can finally decode into a 1 and 0 string. So that's the big challenge. That's all about communications technology and radio and stuff like that, which is why that whole engineering side of NASA goes hand in hand with the actual data taking that the scientists want to do on the spacecraft. Scientists also, in addition to images like the one on the right, it's a beautiful image by the SDO spacecraft, the Solar Dynamics Observatory. We also have one-dimensional data, which is just a bunch of intensity numbers, like the one shown here, which shows the spectrum from an exoplanet called WASP 18b, which was taken by the Webb Space Telescope. And these are very simple types of data. They don't require nearly as much storage because each one of those points that you see there is just a single number. It's not an array of numbers, covering an entire image. So generally, if you're a spacecraft designer, you want less of the data that you're sending to Earth to consist of images and more to consist of these kinds of spectra and one-dimensional things, because you can create and send a lot more of them than you can, if you just use images. But, the thing is that a picture is worth 1,000 words. It's very difficult to take a one-dimensional thing that you see there and turn it into a two-dimensional picture that you see on the right, which gives you vastly more information at a single glance as to what's going on in the object that you're studying. Here you see an erupting prominence on the solar surface, and you see the texture of the solar surface being granular, and you see filaments in the prominence and things like that. Very hard to do if all you're left with are one-dimensional strings of numbers. Sometimes images are the only thing that really makes sense for gathering the right data. Okay, here's an introductory problem. How long does it take to send information, just in general? The old way back a long time ago when dinosaurs ruled the world, we had things called modems, and the first generation of modems that came out were 300 baud. That means they could transmit and receive 300 bits per second, all right? And that was considered pretty darn good. And then, of course, the technology improved and things got faster and better. But anyway, if you took a picture from your old, PCs and IBM desktops, 1,000 by 1,000 pixels in 16-bit color, you'd wind up with about 16 million bits of information per picture. And if you're sending that to your friend, in another city at 300 bits per second, it would take about 56 minutes for you to send that whole picture. And so typically what you would do is you would hit the button on your keypad for send, you go away, mow the lawn, do your laundry, go down to Starbucks, come back, and basically it'll be at 98% complete. And you'd watch for the next 3 minutes as the 98% went to 100. I mean, that's the way it was during most of the 80s. But now, of course, with cell phones, we have 4G and 5G, which are 50 megabits per second transmission rates. And so a 16 million bit image, 1,000 by 1,000 pixels, 16 levels of color, you can now do that in less than half a second, which is sort of tolerable. I mean, I'm willing to sit around for a half a second waiting for a picture of my cat to be transmitted to my daughter. That's not too bad. The Solar Dynamics Observatory, however, really knocks this right out of the ballpark. Its transmit rate down to Earth is 130 megabits per second, and it does this continuously, 24 hours a day, 7 days a week, 365 days for the year. In one day, it transmits something like 1.4 terabytes of data. And you can see the math here. That's basically 86,400 seconds per day times 130 megabits per second. You do the cancellations for the units, and you multiply the things together, and you get 11.2 million bits per day. And of course, 1 bit or 1 byte is 8 bits, and people like to use bytes because they're a bit more compact. So you get 1.4 terabytes of data, and if you multiply that by 8, that tells you the number of terabits of data, because there are 8 bits for the byte. SDO uses this data rate to transmit about 70,000 images to the Earth every single day, or about 1 image every second. Typically, it's a high definition TV imager. Looks at 6 different wavelength bands and takes 1 picture in each of these bands and sends these down consecutively about once every minute or so. So basically, you get a continuous movie of the sun at 6 different wavelengths, so you can see a variety of things happening on the sun at enormous time cadence. I mean, it's just unprecedented. And the resolution is such that on the sun, the resolution of the SDO is about 500 kilometers per pixel. So you're seeing an enormously enlarged surface of the sun, which makes solar physicists extremely happy. Average smartphone stores about 256 gigabytes of information. So the SDO accumulates 1.4 of these terabytes per day. So that's about 5.5 smartphones worth of data every single day. So, for an entire year, that's 1,800 smartphones every year. But, of course, smartphones are not the preferred storage medium for NASA data. They prefer large farms of, data centers, which have these units that store on optical disk and a variety of media, not only terabytes, but petabytes of data. Here we have like 1.4 terabytes of data per day times 365 days in the year, and you wind up with 511 terabytes in a year, which, because 1,000 terabytes is 1 petabyte, is a half a petabyte a year for 1 mission, for 1 NASA mission. As of this year, there are over 213 petabytes of unique data stored by NASA. These are images, these are spectra, these are scans, these are engineering data, a variety of things. So if 1 petabyte is 1,000 terabytes, and 1 terabyte is 1,000 gigabytes, then 1 petabyte is 1 million gigabytes. That's equivalent to 1 million smartphones. If you want to use the smartphone as your unit of measure, that's fine. That's something fairly familiar. But unfortunately, this 213 petabytes is not enough because we have missions like SDO and other missions coming up, like, of course, like the Webb, and still we have Hubble, which produce images by the score. And so NASA needs another 215 petabytes of storage data by the year 2025. Now, the way that this is stored, you can see in the image here, it's stored in a data farm, and NASA has very large data farms, as you can imagine. They look like cabinets, but each cabinet contains hundreds of data storage units. When you're talking about levels of data storage at this level, 213 petabytes, I mean, you're talking about entire buildings. You're talking about an entire building that has to be dedicated to these sorts of storage units. And you might also ask the question, at what point is it going to become so expensive for the electricity to store this NASA data that it's going to be comparable to the electricity that you use to light all of the houses on planet Earth? When are we ever going to get to that kind of a point where we're going to have that much data stored and it's going to cost that much electricity to keep maintaining it? Because of the way things are exponentiating, we might well reach that level in about 100 years at the current rate. And then the question is, well, okay, what are we going to do? I heard that people that mine for Bitcoins, in some places, the electricity usage that they use for the mining, which is a computer-intensive operation, is about 10% of the electrical power in the local power grid, just for mining Bitcoins. So, we're getting into some very expensive technologies and pastimes for a civilization. Gathering data, collecting data, creating new data is becoming, really a very energy-intensive activity for us. Now, on the advanced side, this is sort of the advanced element. We did the introductory part, intermediate part, and now this is the advanced. We talked about sending bits of data across the solar system, but we really didn't talk too much about exactly what that entails. I'm not going to do a show of hands. I would do this if I were seeing you face to face, but how many of you have heard about the inverse square law? All right, well, I assume all of you have, even though I can't see your hands. This is a feature of radiation. It's a feature of gravity, that as you double the distance between the source and where you're located, the intensity of the effect goes down by the square of the distance. So doubling the distance means it's 1/4 as intense. In signal transmission, there are two things that you always keep track of. One is the amount of power that's used to transmit the signal. That's what's provided by the spacecraft, batteries and solar panels. A typical spacecraft transmitter might be 100 watts. Okay, that's not a bad level. The Voyager spacecraft, believe it or not, they operate with 23-watt transmitters to send their data across the solar system, right? Watt is a unit of power, okay? And so that's basically, if you have a 100-watt bulb, you're not getting 100 watts of light from that thing, because most of the wattage that's electrical goes into heating the filament in the lamp. So maybe you're only getting 5% of the electrical 100 watts that's actually converted into light. But we're going to use the 100-watt bulb as kind of a standard candle, and we're also going to talk about the 1-watt flashlight bulb as another thing. Now, that's the wattage of the light. That's the amount of light produced by the thing. But as that light spreads out in space, it is intercepted by a larger and larger spherical area that's centered on the light source. So think of, as the diagram on the right here shows, it shows a portion of a sphere, a spherical surface that's centered on S. And so the area of that surface is 4 pi r squared. And so as you get farther and farther away, that spherical surface increases in area according to the square of the distance. We can then use intensity as power divided by area, and we can talk about how many watts per square meter are flowing through a surface at a particular distance. That's called the intensity. That's the thing that your eye responds to. Your eye does not respond to the fact that you've got a 100-watt lamp. It responds to the fact that that's 100 watts spread out over the area of your pupil at the distance that you are away from the lamp. That's what the retina responds to, and that's intensity. It's also called flux. It's a variety of terms, but I like intensity because it's more easier to work with. So this 100-watt bulb at it essentially covers a 1 meter squared area in its light output, and so it's 100 watts per meter squared. Now, the way that the inverse square law comes into this is that let's take two conditions. If you have a 100-watt bulb placed 10 meters away from you and a 1-watt flashlight bulb placed 1 meter away from you, the intensity of these two is going to be almost exactly the same. And you can figure that out because intensity is power divided by 4 pi r squared, where r is the distance. And so the light bulb is 100 watts divided by 4 pi times 10 meters squared, which is 100. And if you work that out, you get 0.08 watts per meter squared. That's the intensity, that's the brightness of the light that you're seeing from that light bulb at a distance of 10 meters. If you look at the flashlight at a distance of 1 meter, it's 1 watt divided by 4 pi, 1 meter squared. And for that case, you get 0.08 watts per meter squared. The intensities are the same. And that's the experience that you have. If you have a flashlight up close, it can be as bright as a distant, much more luminous light farther away. So this is how power, which is the 100 watts, and the inverse square law are related together to give us the unit called intensity. And this is a very important unit if you're trying to transmit signals across the solar system, because it doesn't matter what the power of your transmitter is on the satellite. It's all about the 4 pi r squared that you're transmitting that power into at the distance of your receiver. And that number had better be above the ability of the receiver to detect, otherwise the receiver will not actually detect the signal at all, and you will not be able to get any information from that satellite. So let's take a look at the Voyager. Voyager has a 23-watt transmitter. Its distance is 120 astronomical units from the Earth, which is, since 1 astronomical unit is 150 million kilometers, or 93 million miles if you prefer, you basically get a distance of 1.8 times 10 to the 13 meters. It's 18 trillion meters away from the Earth. Now, intensity is power divided by area. So what area should we be using? Well, you might think, well, let's use 4 pi r squared, where r is that 120 astronomical unit distance. All right. If we do that, we get 4 pi r squared, where r is this 18 trillion meters squared. We get the surface area of 4 times 10 to the 27 square meters. If the Voyager spacecraft is projecting all that radio energy over the entire sky, over the entire spherical area centered on it, But that's not at all the way spacecraft work. They don't just pump their radio energy into all of space everywhere, but they use parabolic dishes that focus that energy into a very narrow beam, which is shown in the figure on the right. If you just basically pump all this radio energy all over the space, centered on the satellite, that entire figure that you see there would be covered, by radio energy. But instead, it's focused very narrowly into a beam, and there's a main part of it, which is that large central part, and then there are what are called side lobes, where some of your radio energy is invariably going as well. And the design of these transmitting dishes is such that they try to minimize how much of your transmitted power is going into these side lobes and being wasted. You want as much of your power to go into that main lobe as possible, so that as much of your 28 watts of radio signal is focused very narrowly on the destination that you're pointing at, where you want the signal to be detected. Now, the interesting thing is, from the distance of the Voyager spacecraft, the diameter of that beam is about a half a degree, actually a quarter of a degree. That's the radius. And so the deal is, it's pumping all of its energy into an area on the sky that's about as big as the full moon. And it's not putting much of the energy into areas outside of that. So it's highly focused, which is really great, because instead of using 4 times 10 to the 27 square meters, as where your radio signal is going, you can use a much, much smaller number. In fact, this little calculation down here says that it's about 1 million times smaller and 1 million times more concentrated than squirting the radio energy out all over the sky. And that's why we use parabolic dishes on satellites to focus the energy directed at Earth. And that's also why we use parabolic dishes on the Earth to pick up the radio signals from distant spacecraft. Parabolic dishes are the wonder child of radio communications and astronomy. So anyway, what we wind up with, if we do the math, is we have a power of about 23 watts at the spacecraft, and the area that power is being pumped into is about 2.4 times 10 to the 22 meters squared. And that's the intensity of the signal at Earth is just power divided by area. So we get 9.5 times 10 to the minus 22 watts per meter squared. Now, that sounds like a ridiculously small amount of intensity. I mean, it's unbelievably small. There's nothing that you can compare this to in your usual experience of working with radios and things like that. So how do we go about detecting that kind of a weak signal? Well, the cool thing is the meter squared that you see in the denominator there in the watts per meter squared, that can be the area of the receiving antenna. So if you multiply the area of the receiving antenna times this intensity, it'll tell you how many watts of signal you are actually detecting from that spacecraft. And here's the calculation. The radius of this particular antenna here is 35 meters. The area of this is about 3,846 square meters. So the power that's detected at the antenna, that's the power that's relayed down here into the signal area where it's finally measured, is just simply the product of the intensity times the area. And you get a number that's about 4 times 10 to the minus 18 watts. That's 4 billionth of a billionth of a watt. Now, that also sounds like a ridiculously and insanely small number. But in fact, that's a number, that's an amount of power, radio power, that can be very easily detected by this very large radio dish and the incredibly sensitive electronics that are used in the receiver. So that's sort of the way things work in an ideal setting. Now, one thing that I haven't mentioned is the fact that in order to make this all happen, the Voyager has to slow down its telemetry rate. Instead of 156,000 bits per second, which is what it was when it was close to Earth, it has to slow that way down to about 160 bits per second, so that each one of those bits represents more than about 4 by 10 to the minus 18 watts. If it represents less than that, it won't be very easily detected by even this very large radio dish. So that's another thing that happens. Whenever you travel a longer distance in the solar system, you have to slow down the telemetry rate. You might have enjoyed 1,000,000 bits per second squirting a signal from a communications satellite orbiting Earth down to the ground. But in order to detect successfully that very same signal by that transmitter at the distance of Mars or Pluto, you've got to slow down that rate enormously so that each one of those bits lasts a bit longer. I'm sorry to use bit twice in that sentence, and represents more detectable power. All right. You're dividing the same amount of power by a smaller number of bits. So each bit then has more power for you to detect. And that's sort of the way that this whole process works. As spacecraft get farther from the Earth, they automatically slow down their telemetry rates. Of course, that has the unfortunate consequence that it takes longer for you to get the same amount of information back to the Earth. If you're transmitting, Voyager imagers contain 800 lines and 800 dots per line of information. Most of this information is black. So what they do is they compress these images at the spacecraft and send you only the significant information. So that helps because that means you need less information to reconstitute an image. An even better thing that you can do is to forget about sending images at all. I mentioned earlier that scientists also make measurements of one-dimensional information. This can be the intensity of a local magnetic field over time. That's a one-dimensional measurement, a measurement of the field strength every few seconds, and you report that number back as a string of numbers. So once the Voyagers left the orbit of Neptune, one of the first things that they did was to essentially shut off all their imagers, which were big hogs of the spacecraft power anyway. And they reverted to only reporting magnetic field intensities that they encounter, or cosmic ray particle hits, or even dust particle hits that they encounter. So that's what the spacecraft have been doing very successfully for the last, I don't know, 30 years now. And as a result, we're able to look at those strings of numbers in time and determine that the Voyagers have actually left the magnetosphere of the Earth, or the heliosphere of the Sun, and are now in interplanetary space. We saw a big jump up in magnetic field strength and a real big fall down in particle densities, which are signs of their having entered a new regime. So here's what it looks like for the Voyagers as they travel farther from the Earth. At Jupiter, the inverse square law will normalize everything to a Jupiter distance. And at that distance, they were still transmitting at about 115 bits per second as their communication rate. But by the time they got out to Saturn, which is twice as far, and the inverse square law says 1/4 the intensity, or by the time they get out to Neptune, which is 6 times farther, which is 1/36 the intensity, you can see how the bit rates are falling drastically. At Neptune, we were down to 3,200 bits per second, which is about as fast as some of the fast modems that we used to use in the 1980s. Now, with the Voyagers way out at 120 astronomical units, we're down at 160 bits per second. And if we ever get the Voyagers out to 1,500 astronomical units, which would be very exciting, the inverse square law says that the signal strength will be about 1/2 millionth of what it was at Jupiter, and you're going to have to slow the bit rate down to about 1 bit per second in order to collect enough power to be able to distinguish that 1 bit as being either a 0 or a 1, and then successfully reconstitute numbers from that. So that's sort of the upshot, that all these missions together generate a lot of data. The data has to be stored. Storing the data is expensive and has to be planned out well in advance of the mission being launched. You have to build these buildings and stockpile them with the memory modules and procedure for storing this data, because once the satellite gets up there and starts doing its thing, you basically have a fire hose aimed at you. And as a scientist, you're very greedy and you don't want to lose any of that information at all if you can help it. We also learned that transmitting and receiving these signals is all about the inverse square law, and there are certain rules that have to be obeyed. And one of these is that the farther out the spacecraft is, the slower the transmission rate has to become in order for you to detect the signal. Also, you learned a little bit about how the kinds of transmission dishes that are used are extremely important in concentrating the outgoing radio waves into a small area on the sky, rather than spreading it out over the entire 360-degree, or 4 pi spherical surface, which would be very, very wasteful. Also, if you're really clever, you want to design these dishes so that they minimize the amount of power that's lost being transmitted anywhere other than through the main beam of the dish, which I talked about. That main beam, by the way, generally is configured so it constitutes about 70% of the available transmitted power. So dishes are really quite sophisticated and quite well designed these days to maximize as much as possible how much energy goes into that main beam, which makes it easier to detect the signal at Earth. But that's about it for this month. Next month, we're going to talk about citizen science. And of course, there's going to be a little bit of math there, but I'm going to talk a lot more about the individual citizen science programs that are being cooked up for this year in time for the eclipse coming up in April. The main math activity is going to be about aurora and how you figure out how high up the aurora is, which has been a question that stymied physicists through most of the 19th century until somebody figured out how to actually do it. Okay, well, that's about it for my end of this, and I'm now going to open this up to questions.
Thank you, Sten. That was wonderful. I learned so much. I learned so much from you every time. We do have a question in the Q&A. This is from Carolyn Ying. Voyager is no longer taking pictures of planets, but still collecting very useful field and plasma data. With such a small, slow data rate, how long does it take for the data to reach Earth?